Welcome back to Arduino 101. In today's project, we're going to be creating something called an LED chaser. If you've ever been to Broadway or seen any of the Broadway signs with lights that are going all the way around the sign in a following pattern, then you've seen an LED chaser before. If you've ever seen the 1970s and 80s TV show Knight Rider, if you remember, the front of the car famously had a light scanner going back and forth. That's also an example of a chaser. And that's the kind of project that we're going to build today. Just like last time, everything we do is going to be done within Tinkercad, which is, as I mentioned last time, a free Arduino simulator that is able to do a lot of things. It runs entirely online, so you don't actually need to own an Arduino to make sense of this workshop. So before we jump in, I'm going to show you what the circuit does, and then we're going to build it together. Today we're going to cover some new concepts on the code side. Electronically, we're not going to learn much today. We're going to be using the same thing we did last time, which are LEDs and resistors. But on the code, we're going to look at something called a loop, which is a block of code that allows us to run something over and over and over again based on conditions that we give it. Let's have a look at what we're going to build first. If I click on Start Simulation, you can see that we have lights that go back and forth as if they're scanning or sweeping back and forth. Well, that's the goal for today. So let's jump in, start a new project, and get going. As usual, we're going to create a new circuit. And just like last time, the first thing we're going to do is give this a name that makes sense to us. Now, I have created a lot of these, so I'm going to call mine LED Chaser. And hopefully I don't have another one of these. You can call it anything you want. So LED Chaser. We're going to need, for this project, as with every project we're going to do, a breadboard, which I'll drag in right away, and an Arduino, which I'll also drag in underneath. Our basic components for all of our projects, the breadboard, where we're going to plug in all of our electronic components, and down here the Arduino, which, as you know, controls all of the projects we work on. We're also going to need for this one a whole bunch of LEDs. I'm going to plug in 5 of them. So I'm going to pop an LED here, and I'm just going to pop 5 LEDs right next to each other. The closer you put them together, the stronger the effect is going to be. If you had these widely spaced out on a big breadboard, you wouldn't have that illusion of movement. I've got 5 LEDs very close together, as close as I can get them. Also, anytime I plug in an LED, if you remember from last time, we need a resistor. So I'm going to plug in 5 resistors. And just like last time, the resistors are being connected from the cathode or negative side into the negative power rail. Also, just like last time, they're going to be 220 ohm resistors. So I'm going to drag in my resistors, make sure they line up properly. I'll just drag them all in first, and then I'll set the values later. So I'm going to change this resistor value again to 220 ohms. Same thing with this one. And all the way along. Okay. So I now have 5 LEDs packed very close together. I did this pretty quickly. If you found that it was too fast and you want to go back and look at it again, feel free to pause and pick up the video after you're ready. So now I'm going to hook all of this up into the Arduino. I'm going to use the ground up at the top here to plug into my negative power rail and make that a black wire, which is by convention the color for negative. And then each of these LEDs needs to be connected individually to a pin on the Arduino. I'm going to start at pin 8 and go down this way, but you can connect any pin you want as long as they're all in a sequence. I'm going to go from pin 8 here. I'll tidy all these up in a second. 6, 5, and 4. And then, just to make this a little bit neater, I'm going to tidy these up. I'm going to put in some bend points here. Drag this over just to kind of clean this up a bit. This isn't necessary, but It makes it look a lot neater in the simulation. I'm also going to change all of these to red because they're red LEDs. Make that red. And same thing with this one. So if you followed along, you should have 5 red LEDs, 5 220 ohm resistors, and a wire connecting your ground to the negative power rail, and 1 wire going to each of the resistors. And if you've done that, then you have completely finished all of the electronics portion of this activity. Now we're going to jump into code. So as usual, by default, it wants us to go to blocks. I don't want to work in blocks. I want to work in text. And yes, I'm sure I want to work in text. Okay, back in our code editor, the last project we built, we declared some variables. We told it which one was the LED pin. And we told it what to do with the LED pin. So we created something that allowed us to send light to one pin. We also then expanded that and added an RGB, or a red, green, blue LED, and we declared each color as a variable of its own. We could, theoretically for this project, declare a variable for each of these pins. We could declare light 1, 2, 3, 4, 5, but if we wanted to change this circuit later on, and we're actually going to do this, if you want to add a 6th light, we'd have to declare a new variable, and we'd have to change all of our code throughout the entire project to reflect the fact that we'd added one more light. There is a smarter way that we can do this. We can use a loop. And a loop, like I said before, is code that allows you to run, just like the loop function, over and over and over again. We can also tell our loops when we want them to stop. So if we were to define in a project like this, our first pin and our last pin, we could write a block of code, and we're going to do this, that would go from the first pin to the last pin and only run as long as there are pins left inside that range. So we're going to go ahead in our code here and define only what our first pin is, and these are going to be integers, so int first pin equals, the way I've set this up, my lowest numbered pin is pin 4. And our last pin. Now in my case, that is pin 8. Yours might be different. So my first pin, my lowest numbered pin is pin 4. My last pin, which is my highest numbered pin, is pin 8. This is all I need to declare. I'm going to write a code that'll go from the first pin all the way to the last pin. If I added another one, say I plugged in a light to pin 3, all I would have to do, and we're going to do this a little later today, is change first pin, and the same code will run over and over again. Okay, we now have defined our first and our last pins. Let's set this up so we can do something with them. And this is going to be where we introduce the loop. In most coding languages, there are 2 kinds of loops. There's what's called a while loop, and a while loop is something that you have probably encountered in your life without even knowing it. If I were to tell you to drive on the highway until this street ends, I'm telling you, keep going as long as there is street. So you're going to keep driving down the road. You don't have to say, I'm going to drive a meter and then check, and then drive a meter and then check, and drive a meter and check. Your brain instinctively knows as long as there's still road, keep going. That's a while loop. So while there is still road, drive on it. The other kind of loop is a for loop, and that's what we're going to use today. While loops are potentially dangerous in code because if you don't set them up exactly right, you could keep going forever. If I didn't tell you to stop when the road ended, I could theoretically tell you just keep driving straight, and as long as there is whirl, you'll keep driving. Eventually, you'll go off the road. They're very easy to set up what's called an infinite loop, which just never stops and uses up all your resources. A safer kind of loop is a for loop, and a for loop has conditions built in. I'm going to write out the structure, and it's going to look a little bit confusing, but I'll explain it after we've written it out. So it's called a for loop. The first word in this is for. We're going to declare a variable. This is our counting variable, which is an integer. Usually, in a for loop, you use I, which is short for iterator. So my variable, my iterator variable, I'm going to set this to a value. I'm going to leave this blank for now. We're going to come back to this. Semicolon. A condition. So the condition is what you want to check to see if it's still true. So in this case, I is going to be less than a value. We'll come back to that one in a second. Semicolon. And then one of the magic parts of a for loop is telling it the direction we want it to run in. So I, our iterator variable, we want to add 1 to that. There's a couple of ways you can write that. So we could do I equals I plus 1. Technically, this is valid code. However, because adding 1 to something is such a common thing in code, most languages have a shortcut for it. So instead of this I equals I plus 1, we can actually just write I plus plus. So I plus plus means add 1. And then we don't need a semicolon here. And then we're going to close off with closing brackets. And just like functions, you see here we have these curly brackets. We need some curly brackets for our loop. So we're going to open one and hit enter. We're going to close our curly brackets. So this is the basic structure for a loop. We have a counting variable, which is our iterator. We have something we're checking against. And we have a count. So in this case, we're going to go up by 1 each time. Sometimes you want your loop to go up by more than 1, so this can change. However, for our purposes, we're only adding 1 to it. Now we need to define what these are. Well, we want to go through all of our pins and make them an output pin. So our loop is going to start at first pin. So from our first pin, and we want to go until we reach the last pin. And so what this is going to do is it's going to take a variable, so start at a value. The first time this runs, it's going to say, okay, I'm at 4. Is 4 less than 8? Yes, it is. Do what I need to do. Then add 1 to it. It's going to go through again. 5. Is 5 less than 8? Yes, it is. I'm going to do whatever's in these brackets. I'm going to add 1 to it. 6, 7. When it gets to 8, it's going to say, okay, I'm at 8 now. Is 8 less than 8? No, it's not. So it's going to stop. We don't want it to do that. We want it to include 8 as well. Right now, this is only going to go 1, 2, 3, 4 lights. It won't turn on the 5th because when it gets to 8, it's just going to stop. We can change that. And it's really easy to do. If we had an equal sign here, now we have less than or equal to. So as it's checking through, when it gets to 8, 8 is less than, it's not less than, but it is equal to last pin. So it'll include that 8 in its loop. I'll go over that again. We start with our iterator, our I variable here, at the value of first pin, which is 4. It checks to see if 4 is less than or equal to 8, and it is. Does whatever's in the block, and then adds 1. Then it goes to 5. 5 is less than or equal to 8. It does whatever's in the block, and then it adds 1 to it. I'm going to keep going through that until we get to 8. 8 is less than or equal to 8. It'll do what's in the block, and then run it again. It'll add 1 then. Now we're at 9. 9 is not less than 8 or equal to 8, so it's going to stop and end that loop for us. Let's see what we want to do in that loop. Well, pin mode, because we want to turn these to output. Tell it which pin. We are holding in our variable here a value, and we can use that value to our advantage. So pin mode I will be whatever the value is in that loop. It'll start from 4, then go to 5, then go to 6, then go to 7, then go to 8. So it'll hold that value every time it goes through the loop. And we're going to set that pin mode to output. Semicolon. Semicolon at the end of every line, very important. So when we run this code, if I run it, you won't actually see it do anything, because we're not actually toggling any values, but it is setting each one of these pins to output. Let's turn that into something we can actually use. So I'm not going to erase this code. I'm going to comment it out using a multi-line comment, / star, and then underneath it, * / We're going to use some parts of this in our sequence. So I'm not going to erase everything yet. I'm going to copy the same structure because it works for us. So we have a loop here, and we have another loop here. Something I didn't get into last time that is important in code language, and it's kind of an abstract concept, so I'm probably going to refer to this in other projects as well, just to refresh it. Variables in a lot of coding languages have something which is called scope. And a scope for a variable is basically at what level it can be accessed and what level it can be used. Variables we declare up here at the top have what's called a global scope. So a global scope means that anything anywhere in the code, regardless of where it is, regardless of how deeply nested, so how many times it's inside a bracket, can access and use these variables. Global scope variables are useful if you want to set something and then use it at any point in the code. Variables inside a loop, for example, this integer, this I variable here, have a restricted or a local scope. This variable only exists as long as this loop is running. I couldn't, after this loop, call I, it wouldn't hold a value anymore. What's nice about restricted or local scoped variables is that I can declare the same variable every time I want to use a loop. I don't have to say I1 and I2. I can just declare I all over again without affecting the code. If this doesn't make any sense right now, don't worry about it. It won't affect most of the projects we're doing. But you might find at some point that you declare a variable inside your setup function and you want to use it later on and it doesn't work. And if that happens to you, take the declaration, this int, out of the setup function, put it up here in the top. It'll be a global variable and you'll be able to use it anywhere. So importantly, these variables are global. These ones have a restricted or a local scope. So in our loop down here, let's make it actually do something. So we're going to turn the lights on in sequence. Digital write, pin I, which conveniently goes through the loop properly for us, high. So what we're doing is we're going to turn that light on. If I run this, you should see all of the lights go on. Well, there was no delay. It was too fast for us to see. So let's copy in a delay. We're going to add a 1 second delay in between so we can actually see something happening. One light goes on, a second later, the next one goes on. What's happening in our code here? Well, we have, going through our loop, starting at the first pin, pin 4, first one on the right, turning it on and waiting a second. And we're going through that loop one at a time. So we know that our loop is running properly. We're starting at 4, going all the way to 8. However, they're not turning off. And the reason they're not turning off is that we haven't told them to turn off. So we're getting lights going on in a sequence. We're not getting any kind of effect going on. Also, this 1 second delay is a little bit too long for my liking. So let's change that 1 second delay to be something shorter. Let's go with 400 milliseconds. If we run that, it's a little bit faster, and we can use that. Okay, so let's make them actually move in a line here. So we're going to go keep this digital write I high, wait a second, and then let's set it to be low. We're going to turn it on, wait 400 milliseconds, turn it off, wait 400 milliseconds. Now if we run this, we have a very slow moving but definite sequence going from right to left. So 400 was too long. Let's take that down to 200. We now have kind of a jittery, but a definite movement from one direction to another. If we want to create the illusion of smooth movement here, what you need to do, I'm going to stop the simulation. So what you need to do if you want to create the illusion of smooth movement is turn on the next light in the sequence a little bit before you turn it off. It'll create an illusion of smooth movement. I'll do the code and I'll show you what I'm talking about. It'll be clear once you've seen it. The nice thing about a for loop is that we have a variable that we can use and we can control. So not only can I write to pin I can also write to the next pin in the sequence simply by saying I plus 1 is high. So I plus 1 is simply 4, if we're on 4, plus 1, 5. When we're on 5, it's 6. And then I'm going to add another delay. Now, in order for this to work, we need it to be shortly before, which means our delays need to be shorter. I'm going to cut this 200 in half and run this. I now have, it's running pretty slowly, but I now have something that looks a little bit more like they're following in sequence. Light goes on, the next one goes on afterwards, and then it turns off. So we get that illusion of movement from one to the other. Okay. We have used in our code a number more than once. We've written a delay of 200, we've written a delay of 100. If you're going to use something more than once in code, it makes sense to declare a variable for it and call that variable. That way we can change them later. Let's say I wanted to move this faster or slower, and I don't want to have to manually put in the numbers every time. I currently have my short delay exactly half the length of my longer delay, which means we can declare a variable and do the math to hold that. So up here in global scope, because I want this to be accessible everywhere, I'm going to declare a long delay. Again, I'm camel casing. My long delay, in this case, is 200. My short delay is exactly half of that. Now, I can write 100, but programmers generally are lazy. We don't want to have to write out a value every single time. I can also let it calculate for itself what the value of that is, and we can do that using basic math operators. So my long delay, in this case I'm setting manually to 200, and my short delay is going to be half of my long delay. And we can program that into the code. So this one is a short delay. This is also a short delay. And this one down here is a long delay. So if I run this, I now have that same illusion of movement. Now for me, this is running really slowly. You might find with these numbers that yours goes a lot faster. For some reason, Tinkercad is being really slow as I'm recording this. So if you find this is moving too fast and you want to slow it down, all you have to do is put a higher number in your long delay and it'll automatically calculate all of that for you. It's a very quick and easy way to change a bunch of things in your code by only affecting only one value. And that's the real magic of variables in programming languages. All right. I'm going to issue you a challenge now. What I want you to do is, using what we've done here, reverse this sequence. Right now it's going from right to left, which does produce an interesting effect. However, in English and in many languages using the Latin alphabet, we read from left to right. So what I would like you to do is, using this structure, don't delete it, copy it and paste it underneath. I would like you to make this go left to right, not right to left. I will give you about a minute to figure out how to do that. And then when we come back, I'll show you how I did it. So for the next minute, take this sequence and reverse it. So hopefully you were able to figure that out. I'm going to show you how to do it. It's actually really easy. So I'm just going to copy this block. It's a nice convenient block to use. And I'm going to paste it underneath. So right now, if you look at our loop structure, we're starting at first pin and we're going checking against last pin. If we want to do the opposite, we need to start from last pin and go down towards first pin. So we're going to reverse though, as that'll be the first thing we do here. We're going to change first pin to last pin, change last pin to first pin, and this won't do anything because we haven't changed the sequence, we haven't touched enough. We also need to check the opposite. So if we are bigger, if we start at last pin is bigger than or equal to first pin. So we do want to do something there. When we get down to first pin, it is bigger than or equal to first pin. When we get lower than that, we don't want to throw in anymore. We also need to change this to make it go lower. Plus plus adds 1. Minus minus subtracts 1. So if I run this, it now goes in one direction, and then it comes back and everything gets messed up. So there's something going wrong here when it's reversing going left to right. And what that is we're sending signal to our +1, which is turning on the lights that have just been turned off. We want to do the opposite. So we want to subtract 1. Now if I run this, I go right to left and then left to right. So I've now created a scanning effect that can go from one direction to the other. And that concludes our loop. We've created, using some code that was new to us today, a way to set up a sequence of lights to go left to right from right to left. In the next workshops, we're going to use this sequence and we're going to modify it so that we can control the direction of travel. And we're also going to, in our final project, set this up so that we can control the speed of this using a dial. Our basic structure today that we covered was the concept of for loops, a block of code that we can run as long as certain conditions are true and then stop running once those conditions have been met. Our loop function, which has always been part of our code, just runs over and over and over again. It doesn't really have any bounds to it. So we learned how to create a bound to our loop to only run within certain parameters or while certain things are true. Our for loop, as a reminder, has 3 parts in its structure. An iterator variable. We use I as a shorthand for iterator. This variable can really be called anything you want. This is just a convention in code, and it makes it easier for us to type going along. So our iterator variable is a variable that will increase or decrease depending on the direction of the loop. We have our condition. So I'm looking at the backwards loop here. I'm starting at the highest number and making sure that it is greater than or equal to the lowest number in my sequence. And we have the mathematical operation to be carried out. So in this case, we're going to subtract 1 every time. The other direction at our top, we're adding 1 every time. And as with many things, we have curly brackets for our function, or for our loop rather. So our loop this way is going from the highest down to the lowest number. This way is going from the lowest to the highest number. We've also learned that we can manipulate that iterator and use it to do different things. So here we're simply sending whatever the number we're on, we're sending a high signal, or we're writing or turning that on. We can also use the sequence to our advantage. So in this case, we're turning on the next light in the sequence. Down here, we're turning on the previous light, or in this case, the next, because we're going backwards through our loop. We learned a little bit about variable scope. We learned that variables that are declared up here in the very top are global, they're accessible everywhere. And variables declared inside a loop, for example, have a restricted or a local scope. They are only usable within that variable. Scope is something that you will see more of as we go through our code. And as you're doing programming, you will see more and more about scope. I sort of introduced it today, but there's a lot more to cover there than there is time to do in this workshop. We also learned that we can run a loop one way and then run it the other. So we've created a structure that runs forwards and backwards. The final thing that we learned is a good coding practice, and that's to let code, or let the program, do as much of the work for us as possible. And here I'm referring to the delays. We've written a short delay and a long delay, so we don't have to manually plug in the numbers. We've also set one variable to be a function, we've also set the variable to be a mathematical calculation of the value of another variable. So this variable, short delay, is dependent upon the value of long delay. If I put in any number here, short delay will automatically be equal to half of that value. It could be really anything in here, but we're using one value to set, one variable to set the value of the other variable. Well, that concludes part 2 of Arduino 101. In the next part, we're going to add a button to this sequence so that we can control the direction that it's traveling in. If you want to copy this and use it for next time, which I highly recommend, I'm going to remind you of how to do that. In your circuits area, if you want to make a copy of something, all you have to do is click on the gear and duplicate it. I highly recommend, because all of the next parts of this workshop are going to be a variable or a variant on the chaser we built today, I highly recommend that you duplicate this rather than trying to create a new one. It'll save you a lot of time. And also, rather than editing this one, because you might want to come back and refer to this. And that concludes part 2. So thank you very much for joining us, and I hope to see you in part 3.